Hi there, welcome to our assignment 3 as part of the Capstone B project. Today I will be taking you through our project being ankle foot orthosis for children. Introducing myself, Isabella Ashby, who will be covering the executive summary, literature review and parts of the discussion. Reese Pello will be taking you through our semester 1 findings, design process and finally the manufacturing and physical testing results. Lastly, Ethan Hayes will cover a background of the materials, the design development as well as the timeline and project management. Hope you enjoy, thank you. This project addresses the challenges in existing ankle foot orthosis designs, particularly in creating a device that empowers children by enhancing comfort, aesthetics, and functionality. By leveraging additive manufacturing, we aim to produce an AFO that increases user compliance, addressing low adherence linked to discomfort and appearance. Our research informed every stage, from concept generation and prototyping to testing and iterative refinement, ensuring the final design met user needs while adhering to ethical and functional standards. Our literature review highlights the gap in AFO designs that cater to children's empowerment. Most current models focus on function over form with minimal consideration for aesthetics or customizability. Research supports that empowering designs increase user compliance by fostering positive emotional connections. We incorporated insights into how children engage with products, focusing on tactile and visual appeal, and explored industry shifts towards 3D printing, which offers customizability and the flexibility to enhance user engagement. This foundation enabled us to align our designs with the user preferences and manufacturing capabilities.
In the first semester, our team focused on designing an ideal AFO by beginning with children's preferences and translating these into objective, measurable requirements. We gathered insights from family members of children who use AFOs and identified key wants such as light enough for running. After establishing these, we brainstormed ideas and we explored creative themes. Each team member created 12 to 15 initial designs, which we then changed, iterated, and culled until we had 18 final designs. To select the 3 best, we conducted an external survey and an internal critical analysis, narrowing our focus to 3 final designs: a tree, flower pot, and spaceship. Each was evaluated for creativity and child appeal. However, after the break, we were informed by our supervisor that these designs would not function as intended, so instead we took inspiration from what made them special, and each member decided to work on their own creative design. In the CAD design phase, our team collaborated to create 3 distinct ankle foot ortheses, each focusing on user comfort, fit, and stability. We began by taking detailed measurements, including leg and foot dimensions, to ensure an accurate fit. Each design integrated unique features. Design 1 drew inspiration from SpongeBob SquarePants to enhance a child's visual appeal. Design 2 focused on strategic cutouts to improve breathability with a focus on nature. And Design 3 focused on structural adjustments to create a snake-like appearance. Our CAD process was iterative, allowing us to experiment with factors like strap placement, height adjustments, and material thickness while we were making them. Next, we conducted finite element analysis to assess each design's structural performance under a load. We approximated our load requirement to be about 20% of a 70 kilo person's body weight, giving us 137.34 Newton force to apply to the AFO models. We used Fusion 360 to simulate stress, displacement, and safety factors across a quad mesh using 3 materials: nylon, polypropylene, and polyethylene. The FEA highlighted which materials and designs would be most effective in resisting deformation. This analysis helped us narrow down our feasible models to 2 functional ones that we could print, ensuring the AFOs would be both strong and safe for users under normal walking pressures.
We decided to use nylon PA 2200 for the AFO due to its excellent balance of strength, stability, and durability, which makes it suitable for 3D printing. Nylon is lightweight and can withstand repeated stress, ensuring the AFO remains supportive and comfortable over time. Additionally, this material is cost-effective for a product that children may outgrow quickly, making it an ideal choice for our project. While polypropylene and polyethylene has other good properties, the expense outweighed the benefits for the material, especially as the design requirement was to be a low-cost AFO.
For manufacturing, our budget allowed us to print 2 of our 3 designs. While initially planning on using the FEA tested materials, supply issues led to us to select nylon PA 2200 or PA 12 as an alternative to nylon 6. Once printed, we tested the AFO designs ourselves to assess comfort and support, focusing on how the AFOs align with our initial design requirements. Homemade straps with Velcro were used, as well as straps from an existing orthotic device. We aimed to determine if the AFOs were lightweight, breathable, and easy to wear. Though we were unable to test the AFO at RMIT's testing facilities, these trials provided valuable insights into real-world usability, especially comfort and fit. Our findings from FEA and physical testing helped us evaluate each design's strengths and limitations. Design 1 demonstrated a high factor of safety across all materials, minimum deformation, and a user-friendly design. However, in physical testing, it lacked the desired flexibility to make the AFO comfortable for everyday use. Design 2 also performed well in FEA and was much more flexible, but unfortunately was uncomfortable around the calf due to sharp edges and a tight fit. Unfortunately, Design 3 showed excessive deformation under stress in FEA, making it unsuitable to print in its current state. However, small adjustments to the connecting area of the support and footplate would significantly improve these values.
Using finite element analysis, we tested each AFO design with 3 materials: polypropylene, polyethylene, and nylon 6 under 137.34 load to simulate typical gate forces. We focused on deformation, stress, and factors of safety to determine each design's suitability. Polypropylene showed moderate deformation, with Design 1 performing well with only 0.314mm of deformation, and Design 2 also remaining within safe limits. However, Design 3 failed due to high stress. Polyethylene performed similarly with slightly higher deformation. Design 1 again remained within the limits. Design 2 showed acceptable performance, while Design 3 exceeded the material's threshold. Nylon 6 was the most effective, yielding minimal deformation and high factors of safety. Design 1 showed only 0.155mm of deformation, and Design 2 was also viable. However, Design 3 was unsuitable for load bearing. Ultimately, Designs 1 and 2 in Nylon 6 met all safety requirements, guiding our choice for physical testing. This analysis confirmed the durability and comfort potential of these designs for practical use. For physical testing, we 3D printed Designs 1 and 2. Both AFO designs performed well, offering strong structural support, durability, and practicality. Design 2 fit comfortably within a standard shoe, making it suitable for daily wear, while Design 1 was bulkier. Both designs allowed for customization, providing a more personalised, child-friendly aesthetic. However, comfort and fit were primary concerns, with observations revealing minor areas for improvement, such as reducing sharp strap edges to minimise irritation. These insights will guide further iterations, focusing on refining comfort and mobility. Our results underscore the need to balance aesthetics and functionality to effectively support children's physical and emotional needs.
Looking beyond this project, we see several opportunities to refine and advance the AFO design for greater impact. First, we recommend prioritizing hands-on testing with intended users such as children and their caregivers. By involving them directly, we can gather essential feedback on comfort, aesthetics, and usability, allowing future designs to be more aligned with their needs and preferences. Implementing regular feedback cycles would also improve critical insights for refining the device's look and feel, boosting long-term user engagement. Additionally, expanding the customization options would also be beneficial. Incorporating features such as croc-style gibbet holes or changeable colors and patterns can make AFOs feel more personal to each child. A user-driven design approach like this could help foster a sense of empowerment and improve compliance, which is a common challenge with AFOs. Future testing on material strength and durability is another key area for future work. Early-stage finite element analysis and real-world trials would identify any structural weakness, allowing us to enhance reliability. Lastly, partnering with AFO specialists and medical professionals would bring more practical expertise into the design process, ensuring our product meets both functional and emotional needs. By continuing to develop the AFO with these focuses, we can create a more empowering and engaging experience for children using these devices. Overall, the project on designing and constructing an ankle-foot orthesis to empower children has shown significant promise. It is anticipated that the primary goal of enhancing compliance and engagement through an empowering design will be effectively pursued, leveraging innovative structures and user-centered design methodologies. Despite challenges such as limited hands-on experience with AFOs and limited constraints affecting the iterative testing and design stages, the project has maintained a clear focus on its objectives. The iterative design approach and active involvement of external consumers, both children and adults, have been key strengths and have facilitated continuous improvement on the AFO design. While functional aspects of the design remain to be fully validated through final testing, the project emphasis on empowerment is expected to yield positive outcomes. Thanks for listening and I hope you enjoy our final product.